Assalamualaikum warahmatullahi wabarakatuh, and greetings to everyone. In this opportunity, I would like to present a concept paper entitled A Conceptual Framework for Enhancing Student Scientific Creativity in Chemistry Learning by Wimbi Apriwanda Nursiwan, Dr. Chuzairy Hanri, and Associate Professor Dr. Hasniza Ibrahim. Well, in this presentation session, I would like to cover from introduction until conclusion. Okay, we start from introduction. The existence of 21st century learning require essential abilities such as collaboration, critical thinking, creativity, communication, and many more. However, among these skills, creativity stands out as particularly emphasized, as it is considered a crucial competency across various contexts in the 21st century. In field of science education, it called as scientific creativity. Scientific creativity is individual ability to produce many original ideas in order to solve scientific problem. For nearly 2 decades, many science educators have recognized the significance of implementing scientific creativity in science classroom. In the context of chemistry education, there have been limited studies reporting on student scientific creativity level. And unfortunately, the studies indicate that student scientific creativity remains low, or the level of scientific creativity in chemistry education is low level. Therefore, it raises question how to increase scientific creativity in chemistry. So this study aims to develop a conceptual framework enhancing student scientific creativity. The second part is literature review. The first is scientific structure creativity model. There are many scientific creativity models such as PART model, Occurrence model, and Huedi model, or scientific structure creativity model. One of models that includes general aspect of scientific creativity is scientific structure creativity model by Huedi 2002. Based on figure 1, this is scientific structure creativity model. There are three main dimensions, which are product, trade, and process. Product include technical product, science knowledge, science phenomena, and science problem. However, in this study, it's only focused on science problem because science phenomena, science problem, and technical product it's includes into the science knowledge. The second dimension is trade. It includes fluency, flexibility, and originality. Last dimension is process, which are thinking and imagination. Scientific structure creativity model consists general aspect of scientific creativity if we compare to another scientific creativity models, such as scientific knowledge, producing product, producing ideas, scientific problem, and then thinking and imagination, and also involving scientific activities. Thus, this model mostly is used in scientific creativity studies. The second is problem-based learning. Since 1960s, problem-based learning of PBL has gained widespread popularity worldwide. And over time, its concepts have become more flexible and adaptable. As a result, PBL has been extensively implemented and continues to gain traction across various disciplines. There are so many problem-based learning models, such as MIT 1983, Wood 2003, 10 2002, Jensen et al. 2015, and Valdez and Bunahan 2019. So those models are compared according to the aspect that can enhance scientific creativity, such as identifying problem, understanding problem, how this model involves brainstorming, discovery, and evaluation. So the table shows that only 10 2002 fulfill the criteria to enhance scientific creativity. For example, the stages of 10 2002 involve how students identify problem, understand the problem, and involve the brainstorming stage and do this discovery, and the last is evaluation. Therefore, this study used 10 2002 as the PBL model. Okay, so the next part is discussion. As we can see here, there is the figure 2, conceptual framework. There are three main components, namely input, process, and output. For the first component, which is input, it includes teachers' need analysis and the students' scientific creativity that will be a basic to developing of the module. The second component is process. So in this process, it will be module development. Okay, it will be combination between problem-based learning by 10,002 and scientific structure creativity model. Why problem-based learning? Because problem-based learning is student-centered learning. So it can be potential to enhance scientific creativity. However, it needs another component to boost scientific creativity, which is scientific structure creativity model. So each stages will be combined with the characteristic of the or dimension of scientific creativity by Huedi 2002, and I will discuss more detail based on the table too. Okay, for example, for the first stage of PBL, there is meeting the problem. So what the student need to do is must be a characteristic of or criteria of PBL by 10 2002. For example, in the meeting the problem stage, students need to do individual reading, reflection, inquiry, commitment to the team rules and to the group, commitment to the deliberate on problem scenario and problem analysis. So the meeting of the problem, the first step in the PBL is combined with the creative trait, which is fluency, flexibility, and originality. For example, at the end of problem scenario, the students are encouraged to express their solutions, ideas, answers refer to characteristic of fluency, flexibility, and originality. And then for the second step of PBL, there is problem analysis and learning issues. And then step 3, discovery and reporting, and the step 4, solution presentation. So those are integrated with divergent thinking steps by Sun et al. 2002, which are the divergent thinking. It includes association step, decomposition, and combination with the customization, and also scientific imagination steps by Hu et al. 2013. So the activities in the model refer to the main goal of each step. So for example, what the student need to do must be correlate to each other. For example, for the problem analysis and learning issues, students are required to work independently on their own, searching for information through various researchers. So the student need to do brainstorming, analysis of problem, and as a student in the group, they need to make a list of problems among themselves and agree to seek information from any kind of researches, and then coming back with the better informed explanation to the problems and the question process posed. So instead of these stages, there are another activities, which is how to involve student divergent thinking and also scientific imagination. For example, will be combined with the discovery and reporting, and when the present the solution. So the last one is reflection, overview, integration, and evaluation. So based on the PBL by 2002, students reflect on their new knowledge, what they have learned as a result of the problem, and they need to do self-evaluation. And as they are learners and problem solvers, self-directed learner as a member of the team. So it includes chemical knowledge about coloride system is one of topic in chemistry. So is we remember that the conceptual framework there are three main of component, which is input, and then process, and the last one is output. So the last component of conceptual framework is output as the benchmark of the effectiveness of module in enhancing student scientific creativity. And to make sure that module developed can enhance scientific creativity, pre and post test questions are distributed to students to find what extent of module can enhance scientific creativity. So and then the interview also carry out among student and teacher that implement model to see their feedback. So those are the how conceptual framework can enhance scientific creativity. It started from input, how students need scientific creativity, and how exactly the teacher provide activities to enhance students scientific creativity, and what exactly the process, I mean the model that can enhance scientific creativity, and until how the models produce or the module produce can enhance scientific creativity. Okay, so this is the last part, which is conclusion. As we know that scientific creativity is ability that must be possessed by students in facing the demands of 21st century learning. And then to make students able to provide creative ideas in solving problems in the future. Therefore, efforts are needed to increase student scientific creativity, especially in chemistry learning. Because of the close relationship between chemistry and the real life makes it important to develop student scientific creativity in learning chemistry. The result of the literature review that has been carried out produce a conceptual framework that has the potential to increase scientific creativity. So problem-based learning is a model of learning that adheres to constructivism theory, in which student-centered learning is best through problems, because the characteristic of PBL is problem that become the main component in PBL. So students are accustomed to solving future problems. So in addition to train students to express their creative ideas, problem-based learning is combined with the scientific structure creativity model with the three main dimensions, namely creative trait, process, and product. Therefore, the integration of problem-based learning and scientific structure creativity model can be a way to enhance student scientific creativity in chemistry learning. Okay, I think that's all. Thank you so much for the attention. Feel free to contact us through our email, and if you have questions, you can just scanning this barcode and we will provide the answer later on. Thank you so much, and Assalamualaikum warahmatullahi wabarakatuh.